Hey, Chem 30s. So this is kind of a fun lesson. This is using oxidation numbers to actually balance chemical reactions. I think it's fun because it ends up being kind of like a little puzzle that you get to solve, where we take a look at oxidation numbers, we try to make it equal for the loss and the gain, so for the oxidation and the reduction, and then we use that in order to get coefficient numbers to complete balancing. So today's objective is to write and balance equations for redox reactions in acidic and neutral solutions. That's right, we're going back to the whole add water, H positive things. We're looking at acidic mediums. And we assign oxidation numbers where appropriate to the species undergoing chemical change. All right, so balancing oxidation numbers. In a redox reaction, the number of electrons lost by the reducing agent, because reducing agent goes through oxidation, must equal the number of electrons gained by the oxidizing agent, which is going through reduction. The whole base of what we're doing here is making sure that the numbers of electrons that are lost in oxidation are equal to the electrons that are gained in reduction. So by tracking oxidation numbers, by figuring out how much electrons were lost by the Ra and gained by the Oa, and then making that equal by using balancing coefficients, we can then use that to balance the full reaction. So that's what we're getting into today, is using the oxidation numbers and oxidation and reduction to basically balance a full reaction. So here are the steps. I don't like steps. Honestly, steps kind of, I feel like, make things too formulaic. I'd rather just go straight into examples, but just to read through it, and then we'll learn from it from there. So first of all, we are going to assign oxidation numbers and identify the atoms, ions whose oxidation numbers have changed. So we'll assign, figure out what's changing. Use the change in oxidation number, write out the number of electrons transferred per atom, okay, that is going through a change. And then we're going to actually figure it out not just for one atom, but for the reactant. And you'll see what I mean by that. And we're looking at reactants to start off. And then calculate the simplest whole number that makes it equal for the loss and the gain. And then afterwards, once we balance that, then we work out oxygens with waters and hydrogens with H positives. But really, you're going to learn this through me showing you examples. Okay, so let's take a look at this reaction. I actually have a full, nice, neat solution covered up here. I thought about getting rid of it to do my messy writing, but I figured it's probably nice for you to see one example that's actually done in a way where it's just not super ugly with my marker. And I'm still going to make this ugly, don't you worry. We're going to start out by doing some oxidation numbers, but then I'll go to the nice, neat, and ordered solution. So when I do oxidation numbers for this, I would start out with hydrogen with +1, giving me +2 for hydrogen. Sulfur's -2, so that's -2 for the S. Oxygen here is 0, and then here I have -2 for O, so -4, which means S is +4, so I have +4 for that sulfur. And here again I have -2 and then +1. So you can see sulfur is going from -2 to +4, okay? Then I also see that oxygen is going from 0 to -2. So that's my beginning kind of observation. So once I realize that, I will write down, and this is the arrow showing, hey, here's the numbers, and the fact that this is going through oxidation and this is going through reduction. Now I talk about how many electrons happened for each thing. So for the sulfur, it went from -2 to +4. That's a change of 6 electrons. So it lost 6 electrons. It went through oxidation. So it's 6 electrons per sulfur. Now I only have one sulfur here, so the next part seems silly, but that needs to be instead represented for the whole compound, the whole chemical species here of H2S. So it ends up being 6 electrons per H2S because I have one sulfur per H2S and 6 electrons per sulfur, so that's 6 electrons for the hydrogen sulfide. For oxygen, it's a little bit less silly because I realized, okay, I went from 0 to -2, right? So then for the reactant of O2, I have 2 O atoms in O2, so it's 4 electrons that get transferred for every 1 O2 that reacts. So I'm representing this again as the reactant. Okay, so step 2 is for the atom that's going through a change, and then step 3 is for the reactant that's going through a change. Really important you do both of these steps to not make a mistake. All right, so now what I do is I realize that 6 and 4 will meet up at 12. That's the lowest common multiple for both of these. So in order for me to get to 12 electrons for H2S, I need to multiply by 2. In order for me to get to 12 electrons for O2, I need to multiply by 3. So that then locks in these coefficients for H2S as a 2, and then 3 for the O2. Okay, I've now locked that in. So now that I know that, the 2 and the 3, then I can work out the rest. So I have two S's, so I'll put a 2 here in front of the two S's. And now I'm left with H's and O's. So let's go to my O's first. I have 3 times 2 is 6, and then I have 2 times 2 is 4 here for O's. Yeah, and then I've got another kind of H2O, so I'm at 5. I need another one of these H2Os to make that work. And now I've got 4 H's and 4 H's. So that actually works out really well. So now I'm all balanced, it works out. There's my final answer. Step 5 would be that if I end up having anything that's the same on both sides, like for example, I often could have water on both sides or hydrogen ions on both sides, then I would cancel that out. Okay, so it would be removed from one side and then I would subtract it from the larger side until it works. I'm sure we have an example where that will come into play here and you can see what I mean by that. Okay, so let's actually take a look at this example and try it out. I just want to make this a little bit larger. Oh no, it's not easy for me to make it larger when I'm in the middle of the video. Disaster. Just pretend like this isn't happening, okay? All right, let's do that. Let's enlarge this. And there we go. We now have a little bit more space to work, and it will hopefully be easier to see. So for oxygen here, I have -2 times 3 is -6. I need to come out to -1. So my bromine will be +5 to make it equal -1 for the charge. In C2H6O, I have +1 for hydrogen, -2 for oxygen. So I have +6, -2, which means that my carbon has to come out to -4, which makes carbon a -2 for an oxidation number. In CO2, I have -2. I have 2 of them, so I have -4. That means that this carbon, because it comes out to a total of 0, has to be +4. So +4. And I know I'm rushing through these oxidation numbers. At this point, I'm assuming you have this skill. If this is still an issue for you, hey, go back to the oxidation number video or pause it, try it out, and then watch what I'm doing, right? Because right now my focus is not on the oxidation numbers, it's on teaching you the balancing with it. So +2 for hydrogen, that makes this +1. All right, so what's changing? Well, bromine is changing. It goes from +5 to -1. I don't want to draw an arrow. It's going to look so messy. But bromine goes from +5 to -1. And then carbon is going from -2 to +4. So here's what I'm going to do. I'm going to say for each bromine, this goes through, and actually I want to do this a little bit differently. It goes through a change of 6 electrons per bromine. Okay, now +5 to -1, important that you realize that is a difference of 6, not 4, but 6, right? I add 6 electrons in order to get from +5 to -1. Now I have 1 bromine per BrO3 minus, so it's the same number for the reactant. It's still 6 electrons per BrO3 minus, but still important to show that I thought about that it's a 1-to-1. In this one, it's going to be more of an issue because I have -2 to +4. So that's a change of 6 electrons per carbon. But I have 2 carbons in each one of these. So it's actually 12 electrons for the reactant per C2H6O. So I have 6 and 12. So that means that in order for me to make this equal, I'm going to need 2 of these, and I'm going to need 1 of these. So now I lock in my numbers for my reactants. I now have a 2 here, and I have an unwritten 1 here. And now I can tackle the rest of this. So I have 2 bromines, so I can put a 2 in front of bromide. I have 2 carbons, so I can put a 2 in front of CO2. And now if I take a look at my hydrogens, I have 6 hydrogens, so I can put a 3 right here in front of the hydrogen to get to 6 hydrogens. Now let's check my O's. I have 2 times 2 is 4, plus 3 is 7, and here I have 2 times 3 is 6, plus 1 is 7. Another way that I can double check this is I can check the charge. Total of the charge on the left is 2 negative, and total on the charge on the right is 2 negative. So I'm done. It works, it balances, fantastic. So far, we're not dealing with any of the aqueous medium water stuff. We're going to see that later on. Okay, so now if I take a look at this, I can do the exact same process. I think that you should pause it, give this a try, yeah, and then come back and see the answer. So go ahead and try it out now. And here's the answer. I have -2 for oxygen, so +1 for hydrogen, that makes nitrogen +5. -2 for O, sulfur is +4. -2 for this, +1 for this, that makes sulfur +6. And then I have -2 for O, which makes nitrogen +2. All right, so here's my change. I have 3 electrons per nitrogen, and I have 1 N in every nitric acid. So I have just 3 electrons, the same number per HNO3. So it's the exact same because I have only 1 N in HNO3. When I look at sulfur, it goes from +4 to +6. So I have 2 electrons per sulfur, which means that I have 2 electrons per SO2 because again, it's the same number. I have 1 sulfur in each SO2, so it's going to be 2 electrons per sulfur, a change of +4 to +6. So 3 and 2 are going to meet up at 6 in total. So I need a +2 for nitric acid, and I need a +3, I shouldn't say positive, I just need a 3 for SO2. So I'm going to lock in those coefficients for the reactants. I have a 2 here, and I have a 3 here. So now I can make sure that the rest of the atoms work out. I have 2 N's, so I can put a 2 in front of NO. I have 3 sulfurs, so I can put a 3 in front of H2SO4. And now let's check the rest. I have now 6 H's, and I have, oh, this is fun. It doesn't work. And I have 2 H's here, and then if I look at O's, I have 6 O's plus another 6, which is 12, and I have 12 14 O's over on this side. So this is where the fun begins. I need to actually add in some waters here to make this function, to make it work. So what I'm going to do is I'm going to add 2 waters to the left-hand side. And I know I kind of have to sneak it in there because I don't have this written out in long format, but I'm going to put 2 waters on the left. And now that gets me 2 times 3 is 6. Plus 6 is 12, plus 2 O's is 14, and then here I have 3 times 4 is 12, plus 2 is 14. So now my O's are good by adding a little bit of water. Now let's look at my H's and see if they're okay, because that would be the last step. I have 2 H's over here, plus another 4 is 6, and I have 6 H's over here. So I don't have to add any H positives, which is good because it doesn't say anything about acidic medium, but I do have to add these 2 waters. So just to make this maybe a little bit less messy, let's write out our final reaction then. I would have 2 HNO3 aqueous plus 3 SO2. Oh, it lagged. Let's try that again. 3 SO2 gas plus 2 H2O liquids makes 3 H2SO4 aqueous and 2 NO gas. That is my final balanced reaction. And I know that I have water at my disposal because I have aqueous steps. So of course I have water that can be a part of the reaction because I have aqueous things. Okay. Another example, this is a word one, and you'll notice the addition of acidic solution. So I know that I have H positive aqueous at my disposal. Again, I would take a minute, try this out, read it over, go over it, and then take a look at the solution. All right, so pause now, and here's the answer. I have chlorate ions, so ClO3 minus aqueous, And we'll use two colors here, one for the reaction and one for the oxidation numbers. And iodine reacts, so iodine I'm just going to write out as I2 solid. It's an acidic solution, but I'm not including that yet. And I produce chloride ions, so Cl minus aqueous, and iodate ions, so IO3 minus aqueous. Okay, so let's get a different color going for my oxidation numbers to add some stuff in. So for oxygen, I have -2 times 3 is -6. So chlorine has to be +5. For I2, it's an element, so I'm looking at 0 for that. Chloride is -1. And then here I have -2 for O, which is -6, which means iodine has to be +5. So if I look at iodine, for each iodine atom, it goes from 0 to +5. So I know that it's 5 electrons per 1 I, but I have I2, so it's 10 electrons per I2. And then for ClO3 minus, I go from +5 to -1. So I have 6 electrons per Cl is the change, right? 5 to -1, which means that I have 6 electrons per ClO3 minus, because again, I have just one chlorine in the chlorate. So what's the lowest common multiple between 6 and 10? Well, that's going to be 30. So I need 5 of these, and I need 3 of these. So I'm going to have 5 ClO3 minus, and I'm going to have 3 I2s. And again, the idea behind this is that the number of electrons that are gained have to equal the number of electrons that are lost. So in this specific scenario, iodine is losing electrons and it's giving them to chlorine. So the number of electrons has to equal out. And in this scenario, that is 30 electrons are being transferred with how we will end up writing this reaction. So I have 5 and I have 3. These are now locked in. So that means that I need 6 of the iodates, because 6 I's to match the 3 times 2 is 6 I's. I have 5 chlorines, so I need 5 of these to make chlorine work out. Now I can focus on oxygen and then hydrogen. So for oxygen on the left, I have 5 times 3 is 15, and over here I have 6 times 3 is 18. So I need 3 waters on the left in order to get my 3 O's that I'm missing. And now I have 6 H positives or 6 H's on the left that I need to actually balance out on the right with the 6 H positive aqueous over here. Okay, now I can double check my charge to make sure it works out, right? So on the left, I have 5 times 1 negative. So it's just a 5 negative charge overall. And then on the right-hand side, I have 5 negative with 6 negative and then 6 positive. So that also comes out to 5 negative. So this looks like a great answer. I'm confident it works because of the fact that the charge on both sides equals out. All right. Do we do one last one? That video will just show up horribly. I feel like most of you right now will probably be in a good place with this, but if you want to see another example, hey, fantastic, let's go ahead and do this now. Got an extra word there of, so we'll just leave that covered up. Balance the chemical equation for the oxidation of ethanol by dichromate ions in a breathalyzer to form chromium-3 ions and acetic acid in an acidic solution. So I once again actually have access to my H positive with the acidic solution. So I have ethanol, which is going to be C2H5OH liquid. We'll actually do that aqueous, as it does dissolve in water, by dichromate. So that's Cr2O7, 2 negative aqueous. In a breathalyzer to form chromium-3 ions, so I end up with Cr3 positive aqueous and acetic acid. So that is going to be CH3 COOH aqueous. I'm going to have to actually do afterwards, I think, some sneaking in of the H positives in the waters because I didn't leave enough room here, but you'll get the idea as we go through. So let's switch to red now for oxidation numbers. So when I take a look, I have +1 for hydrogen here. So I've got +1, +5 from these. Oxygen's -2, -2. So that means that my hydrogen here is going to have to come out to -4 to make that work. So each carbon will be -2 for an oxidation number to make this come out to 0, right? +1, -2 is -1. Yeah, that works out. Cr2O7, I have -2 for oxygen, so -14 for the O's. That means that chromium will have to be +12 in total, making each chromium +6. This as an ion is going to be the same, so +3. And then for acetic acid, this is actually kind of a fun one. I have -2, -2, +1, +1. So I have +3 from here. I have a -2 and a -2 from the O's and a +1 from the hydrogen. That already works out to 0. So that means carbon is actually 0 for an oxidation number here and here. And again, both carbons are identical. We're treating them the same. All right, so what do we have? Well, we have -2 going to 0 for carbon. So we have 2 electrons being transferred per carbon, but I need to look at the full reactant, which is 4 electrons per C2H5OH aqueous. And then I have from 6 to 3 for chromium, so I have 3 electrons per chromium, but then I have 6 electrons for the dichromate Cr2O7 2-. So now I look at 4 and 6 and think, well, where do they meet up? And they meet up at 12. So I need 3 of these, and I'm going to need 2 of these to get to 12 electrons. So that locks in this coefficient as a 2 and this coefficient as a 3. So now I have 3 times 2 is 6 carbons. So I'm going to have to put a 3 here to get 6 carbons, right? 2 times 3 is 6. I have 2 times 2 is 4 chromiums, so I'll put a 4 here in front of Cr3 positive to get 4 chromiums. And now what I'm looking at is oxygen. So I did the other atoms first besides H and O. Now I look at the O and then the H. So on the left-hand side, I have 3 O's plus 14 O's. So I'm looking at 17 O's on the left. And on the right, I have 3 times 2 is 6. So I need 11 waters on this side in order to balance out the oxygens. So 11 H2O liquid is hanging out in the products. And now I can take a look at my hydrogens. So for hydrogen, I have right now 3 times 6, right? 5 plus 1 is 6. So I have 18 hydrogens on the left. And then on the right, I'm sitting at 3 times 4 is 12, plus another 22, because 11 times 2 is 22. So I'm looking at 34 hydrogens. Oh, it's so many on the right. So between 18 and 34, I am missing 16 hydrogens that I have to add to the reactants. So 16 H positive aqueous will be a reactant here. So now let's take a look at our overall charge just to double check our work and make sure it's good. So on the left-hand side, this doesn't have a charge. This has a charge of 4 negative, and then I have 16 positive here. So that gives me 12 positive for an overall charge in reactants. And then in the products, I only have one thing with a charge, which is the 4 chromium 3 ions. So that gives me 12 positive for a charge on the right. So I feel good, feel confident that this is a good solution and it works because the charges equal out on both sides. That was a tough one. That's involved. It's crazy. Okay, anyways, that is balancing redox reactions with oxidation numbers. Have a good rest of your day.